Yeah, thank you for your support. Last lecture, and 1, 2, 3, 4, 5. I have 6 of you here, at least at this point of time, we have 6. All right, so what do you expect from today's session? Tips? I'm sorry, you may be disappointed. No tips. You have any questions? I was just asked about the whether it's necessary to have a graphic calculator. We don't have any restriction on the calculators, and we prepare that. I think we also give you some of the statistical tables, not all. That you find it in the files or the work bin. All right, so it's similar to those. So so you still can get the answers even without a graphic calculator. All right. There are short questions. I've got how many? Likely 5 to 6 short questions. No choice. You have to answer all. Answer all questions. So questions have parts. So you have to answer all the parts. All right. So revision. Let's begin our journey of revision. Okay, so what is the first chapter? First chapter is on events. So you have to be aware of the operations of events. So a simple one is two events, A intercept B and A union B. All right, and of course we also talk about the sample space. That means a set of all possible values and an empty set. Also, we talk about complement. All right. What else? Okay. So a lot of times, because these events are basically as sets, so you can use the Venn diagram to represent some of the operations of the events. So, for example, we know that A union A complement equal to the sample space, or A intercept A complement equal to empty set. I think one of the very useful properties is that an event A, all right, can be considered as divided into 2 parts. One is something common to B, and of course there's something common to B complement. All right. So in that case, we union these 2 parts. Okay. So these 2 events, A intercept B and A intercept B complement, these are mutually exclusive events. So it's very important. So the concept of mutually exclusive events, so you have to know the properties and how they are used. All right. We say that 2 events are mutually exclusive if A intercept B equal to empty set. All right. And yeah. So we also have this Morgan's law. Basically, it's saying that A union or A1 union A2 union up to AN, the complement of this. That means we try to union all this event and take the complement, which means that we look at those elements. It does not belong to any of these AIs. So it's equivalent to, it does not belong to A1, it does not belong to A2, and so on. So it's common to all this. So it's the intersection. So if you understand the rationale, the definition, it shouldn't be difficult to get this identity. All right. So similarly, I think the intersection, the complement of it is equal to A1 complement. Okay, I'm sorry. I also use a prime to represent complement. So here I use C to represent the complement. So in fact, they're the same thing. All right. Okay. So union all this A and complement. All right. What else? Okay, so these are some of the operation of events, and in order to do probabilities, we need to we need to define the probabilities. So we also learn how to count. All right. So the important thing in counting is, or in probability to do counting, is the permutations and the combinations. Okay, you may have formulas. Permutation, permute R objects out of n objects. So this one is equal to n factorial divided by R factorial. Basically, it's n times n minus 1 times up to n minus R plus 1. All right. Okay, there are formulas here, but I want you to understand how these formulas are used. So basically, permutations means that you try to arrange R objects taken from n objects. All right, to arrange them, and the order or the position of the objects are being considered. So something like, for example, the arrangement of 1, 2, 3 is different from 2, 1, 3 because the order are different. Although the same three subjects are, three objects are used. Okay, another one is combinations. In this case, the order is not important. We just try to select n objects out of R objects. So in this case, the number of ways that we can select select R objects out of n objects is n factorial over R factorial over n minus R factorial. Why? Because altogether, all right, this is the number of ways. So for example, this is one way to do it, but then there are okay, I think I make, is this correct? Yeah, n minus R, all right? Thank you. Yeah, n minus R. Why? Because this is the correct one, so I have to cut out the n minus R factorial. So I have to divide by n minus 1 factorial. Okay, so this part basically is how to permute R objects out of n objects. And because the order is not important, so we have to count out of these R objects how many ways that we can arrange them. So it's R factorial. And all this will be counted as 1. 1, 2, 3, 2, 1, 3, 3, 1, 2, all this. All this will be counted as 1. So we just count how many of them. So that's how we get this formula. So you have to know how to use this formula. All right? Not just applying the formula, but understand what this formula means. So it's permutation and combinations. All right. Okay. Just sidetrack a bit. So this we use n minus R to represent C. Choose n minus R objects out of n. This is the same as n choose R. So it looks very funny, but we can prove mathematically that this is correct. But from combinatoric point of view, it basically said you have n objects. How many ways you choose out of this n object, choose n minus R of them, is the same as you choose R of them. Because basically, just look at which part you are looking at. Either you choose R out of this n, or you choose n minus R. When you choose a particular n minus R objects, the remaining R is the option or the choice for the R objects. So it's 1-1 correspondence. So the number of ways to choose R objects is the same as choose n minus R objects. All right. And this one, okay, is even. So the way that we choose n choose R is the same as n choose I naught R minus 1. All right, and then okay, maybe I okay. Forget about this one. It is n. Try to prove that or try to show that from combinatorial point of view. Choose R out of n is the same as n minus. Is this correct? No, I ask you to pick R objects out of n objects. Of course, it's not correct. All right, but you can think of it. I divide these n objects into I'm sorry, I made a mistake here. N minus 1. So I divide this into two parts. N minus 1, 1, choose 1. So a particular object, all right, a particular object, I choose it, all right, and then the remaining one I choose R minus 1, all right. Of course, you can have choose R objects out of the n minus 1 objects. So what's the difference between these two? The first term is a particular object is included in my combination, or I have to include it in my choice of R objects. All right, so that I choose that in, and then multiply the remaining one, I choose R minus 1. All right, the number of ways to choose R minus 1 out of the n minus 1, so I call it. All right, but there's another situation. This particular object is not included, not chosen. So in fact, if it's not chosen, then where I got this R objects? So it will be from the remaining one. So the scenario is this one. I asked, okay, I have this n objects. I choose R objects out of it. So I consider a particular one. Okay, this particular object, let me call it A. So this one in the chosen sample or chosen set, then the remaining I have to choose R minus 1. So this is the part. All right. While this one is 1, 0. That means this particular object is not included in the object. All right. So the idea of this identity is that, okay, I break down this, look at it from a different angle. This one, you ask me to choose R objects out of n objects. I divide it into two parts. I look at a particular object, see whether it's included or not. If it's not included, then I have to pick the R objects from the remaining one. If it's included, I would pick R minus 1. So there's a number of ways to get all this. I add them up. So my point is, you can look at it from a different angles to come up with a different identity or different equations. All right. Then we try to define the probability, and one very, very important way or foundation for us to define the probability here is that we look at the outcomes. They are equally likely. So for example, a simple example is like 4D. Pick a number out of 000 to 9999. All right? So we just pick one number. So if the number turned out to be the winning number, then we win. All right? So in this case, to us, it's either our number win or lose. So it's only two possible outcomes, but they're not equally likely. The equally likely event or is the numbers. So 000, 0 and 0001 are all these 10,000 numbers have equal chance of being selected. So the basic or the foundation of this way of computing probability is assume that the outcomes are equally likely. So the set A or the event A, you just have to count how many sample points favor A in the event A. All right. So so we need equal likely. So remember axioms of probability. What are these? It's saying that for any event, the probability of event has to be between 0 and 1. So if you calculate a probability of certain event exceed this range, something wrong. Second axiom is that the probability of the sample space is equal to 1. That means the chance of all possible outcomes should be 1. All right, and all right. So this is 1, 2, and the third one is saying that if you have infinite number of mutually exclusive events, then the probability of union of all these events is equal to the sum of these probabilities. All right, so infinity. So if they are mutually exclusive, then union of all this, the probability of this event is equal to the sum of individual probability. So basic idea is that, okay, if they are mutually exclusive, then I just add up all the probabilities of all these individual events. That will be the same as the probability of the union of all these events. All right, so this is important. Properties of probability. All right, so I think this one is very important and you have to know it. Probability of A union B is equal to probability A plus probability of B minus probability of A intercept B. All right, this is one of the most popular or frequently used properties of probability of two events. Probability of union of two events is not equal to, does not equal to probability of A plus probability B, but equal to probability A plus probability minus the intersection. If I may draw the Venn diagram to show the idea, not a proof. So the union of this part, the sample points in this part count twice in computing this one. So that's why I have to subtract the probability of A intercept B. All right, and of course this one can be extended to probability of A union B union C. So you have to know how this can be represented. So it's more complicated. So it involved, of course, A, B, C. Then you have to minus the overcounting here. So minus probability A intercept B, minus probability of A intercept C, minus probability of B intercept C. But unfortunately, once you do this, you subtract too many. So you have to add back the A intercept B intercept C. All right. So this one can be repeated for 4 events and so on. All right. Just remember, if an event is a subset of the other event, then the probability of A must be less or equal to probability of B. It's a subset or proper subset. All right. What does it mean? It means that all the outcomes in the event A also appears in event B. Then we say that A is a subset of B. All right. Yeah. So if you for this formula, this is true in general, but in a special case, the special case is when A intercept B equal to empty set. And with a name for it, we call it mutually exclusive event. All right? Then in that case, the union event is equal to the sum of A plus sum of B. All right? So equal to that. And so you can use that. So sometimes when we try to compute the probability of A, so it's equal to the number of sample points in A over the number of sample points in S. That's all possible outcomes. Basically, denominator is all possible outcomes. And remember, when you talk about these outcomes, it has to be equally likely in order to use this formula. All right? So just the 4D scenario, winning or losing is not equally likely. So it's not half. All right? If you just buy one number, the chance of winning is 1 over 10,000. All right? If you buy 10 numbers, you have only 10 out of the 10,000 outcome. So the chance is 1 over 1,000. All right? Then we have this conditional probability. This a little bit complicated because some will find it very confusing. But basically, it's very commonly used technique or properties of probability. So we have two events, and we're asked, okay, if we know one event occurred, then what happened to the others? So the event becomes A intercept B divided by probability of B. Or you can look at it. All right? So probability of A basically is the number of sample points in this A compared with all the possible sample points in the sample space. But then now if you are told that B has occurred, so it's no more all the outcomes in the sample space, but we restrict our attention to only B part, the B. Because we know that B has occurred. So suddenly our sample space reduced to B. All right? So we just look at this part, which is common to A and B, and look at it, how this compare with the sample points in B. So that is the idea. All right? So you have to understand the formula and this to use to compute the conditional probabilities. All right? You just remember, conditional probability, all right, is still a probability of an event. So it satisfies all the axioms of probability or the properties of probabilities. All right. So from here, so we can consider the probability of event B is equal to event A intercept B. Sorry, probability of A intercept B is equal to probability of B times probability of A given B. So this gives us a way to compute the joint probability. All right. So you want A and B together, then first of all we look at the chance of B occurs, and then times the probability of A occurs given B has occurred. All right. So this is called multiplicative rule, but the name is not important. All right. And there's another useful idea. It's called law of total probability. All right. So what does it mean? It simply means that, all right, I partition the S into parts. All right. All these parts are, I call it BI. So BI are the partition of S. And then if I look at the chance of A, then I look at A common to B1, A common to B2, and so on. So the probability of A, okay. I think in my lecture notes I use AI for this one, and this I call it B. So probability of event B is equal to probability of B common to A1 plus B common to A2, and so on. All right. And then each one is equal to A1 times probability of B given A1 plus probability of A2 times probability of B given A2, and so on. All right. So the idea of total probability is nothing but just saying that, okay, I partition my A, my B into different parts. This part common to A1, this part common to A2, and so on. And remember, A's are all mutually exclusive events. Not only just mutually exclusive, but it needs to union equal to the S. So we call that a partition. Not just they are disjoint, all these AI are disjoint, but when union all of them, it has to come up equal to S. All right? So these are the criteria that you need in order to apply this total probability. A very simple example is this. Probability of B is equal to probability of A times probability of B given A plus probability of A complement times probability of B given A complement. So this is a very simple way to partition the S into A and A complement. So they are mutually exclusive and union equal to S. And then I look at the part B common to A and also B common to A complement, and then add them together. All right. Okay. So derived from that, then we have this Bayes theorem. So what does Bayes theorem say? Bayes theorem basically saying that, okay, if now, the other way around, if I know that B has occurred, what is the chance that AK occur? All right. So just now when we derive the total probability, we are looking at A's and then followed by B. So now we know, we are saying that B has occurred. So now we ask, what is the chance that you got AK? So follow from the definition of conditional probability, this is probability of AK intercept B divided by probability of B. Right? So I just make use of this total probability, substitute into the denominator, so I got this Bayes theorem. All right? So Bayes theorem is nothing new. It just applies the conditional probability. So the idea is that you can think of it like this. Usually we go step by step. So first of all, we look at all the A's. So in other words, we start with A's. All right. So maybe A1, A2. So what are these probabilities? All right. Then if A1 occur, what's the chance that you will got B or you don't got B? You got B or you don't got B, and so on. All right. So this is the picture or a tree diagram to illustrate the event. But, all right, what happens if we are told that B has occurred? So what is the chance that it comes from a AK? A particular one is AK. All right, AK, B and B complement. So we know that B has occurred. So it can be here, can be from this path, can be from this path, and can be from this path. So we know that what is the chance that it comes from this path through AK. So that is what the Bayes theorem says. So you know something happens at a later stage, and you try to modify your belief in the previous stage. All right, so we apply this Bayes theorem. And there's also one very important properties about events is independent events. All right? So remember, two events are considered independent if and only if this is true. All right? Don't use your intuition, all right, and think that, oh, these two events are independent. You must be able to show that this is correct. That means the joint probability equal to the product of the marginals, or product of these two events. Of course, this one, another form to say it is that probability of A intercept B is equal to probability of A times probability of B given A. All right? So this is another way to say that A and B are independent. What does that mean? It means that the probability of B is the same as the condition probability of B given A. So in other words, it doesn't matter whether you have knowledge of A, the probability are the same. In that case, we say A and B are independent events. All right? Because if these two are equal, then this, from the definition of conditional probability, so is equivalent to this statement. So in that case, they are, A and B are independent. All right? So I think we discussed, and I give example in the lecture notes. These two are not the same, and I give you examples. Sometimes it's this and this. So one may not imply the other one. So I have some example to illustrate that. All right. So yeah. Okay, then we also talk about, this is independent for two events. So for n events, n mutually independent events. We discussed this before. So if you have A1 up to AK, AN, n events, all right. If we want to say that they are independent, mutually independent, then that means any subset taken from this set, all right, they are independent, all right. So in other words, any form A1 intercept AK, and this is true for any combination, any K and any combinations. All right, so it's a very, very, very strong definition. Okay, you should not just say, oh, for this set, I just take any two and show that they're independent, and I concluded they're mutually independent. No. All right, I have examples to illustrate this in the lecture notes. So you just have to remember, for independent event, for 2, it's very simple. But for 3, then you have to check. Any combination of 2 events that are independent, and 3 events that are also independent. All right, then the chapter 2. Yeah, chapter 2, random variables. So you must know what is a random variables. X is a variable, and it's also attached to it with a probability or some kind of measure of probability. So, so the behavior of it is represented by a PDF or a probability function. So a random variable basically is to map the points from sample space to the real line. So example is that toss a die. So the outcomes are 1 to 6. Then we map this value, or maybe this is not a good example. Toss a coin. So the outcome is head and tail. Or toss 2 coins. Then the outcome is head, 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 tail, tail, head, and tail, tail. So we try to map this to a real line, to some real number. So that's a random variable. All right. So for example, X represents the number of heads. Then it maps to 2, 1, 1, and 0, where X represents the number of heads in tossing 2 coins. All right. So once we know the definition of what is a random variable, then we will like to describe the behavior of random variable through this f of x. Oh, there are 2 types of random variables: discrete and continuous. So you must able to identify whether the variable is discrete or random or continuous. It's important for you to compute or to answer the questions. For discrete, we have to do summation or work on the sum of things like that. While for continuous, we use integration. Like find the probability x within certain range, you do integration for continuous random variable, while for discrete it's not. You do the summation. So in order to be a probability density function or probability function, you must have this property. F of x must be greater or equal to 0, and sum f of x or integrate f of x dx from minus infinity to infinity must equal to 1. All right. So sum over all the x of f of x equal to 1, or integrate from minus infinity to infinity f of x dx equal to 1. Now here I have to warn you, when you do the integration, all right, make sure that when you do integration, all right, so the f of x, all right, if you have different forms of f of x, for example, I say, oh, f of x equal to, let's say equal to x, where x is between 0 and where x is between 0 and 2, all right, where x is between 0 and 2. maybe on the safe side, I put a C here, all right? So it's like that. Now then, this form of the PDF is only valid when x between 0 and 2. So it will be 0 otherwise. All right? So when you do an integration, you cannot say, oh, I integrate from minus infinity to infinity cx dx. So this is wrong because cx is not valid when x is outside the range of 0 to 2, for example. All right? So you have to be aware of that when you do the integration. So, for example, if you are asked to find probability of x between 1 and 5, if the PDF is given like that, then if you follow the definition, it's from integrate from 1 to 5 f of x dx. But unfortunately, f of x does not equal to c times x. It only equal to c times x when x is between 0 and 2. Outside that range, it will be 0. So you have to break down your integration into parts that work separately. All right. So that's one way to do it. And yeah. So another very important thing is for continuous random variable, the probability of x equal to a particular value is always 1. So it doesn't matter whether it is greater or equal or just greater than. All right. So you have to be aware of that. And we also have this cumulative distribution function, which denoted by capital F, which is probability of the random variable less than x. All right. So it's equal to integrate for continuous case is integrate this one. For discrete case, you sum over all the ft such that t is less or equal to x. All right, depends whether it's continuous or discrete. Okay, so so it's important that you want to know something about the random variable x. Either you know the PDF or probability function, that means the lowercase f of x, or you know the CDF, okay, the CDF. So in other words, these two are just different way to represent the behavior of the random variable x. So in other words, you need to know how to convert from one to the others. So getting the CDF from f of x, so it's easy. So you just do the integration or summation, all right? Then how about if you are given the CDF, how to convert to BDF, or given the CDF, how to get the probability function? So you have to know how to do it, right? I think for continuous case, then you may just differentiate it, all right? Do differentiation. For discrete case, then you really have to compute the probability, all right? So f of x, which is probability for discrete case, is equal to this, which is equal to probability of x less or equal to x minus probability of x equal to x. Sorry, less than x. All right, it's the difference between these two probability. So probability of x less than a little x means that you are finding the CDF at a number which is slightly less than x. So we rewrite it as f of x minus f of x minus. X minus means a number is smaller than x. All right. So little f of x and capital F of x, you have to know how to use them to compute probability as well as how to convert from one to another. All right. Then we also talk about expectation. So you have to know expectation. So in general, expectation of function of x. So this is equal to sum of gx f of x or integrate gx f of x dx. So in particular, gx equal to x, that is the expectation of x, or variance of x, then gx is equal to x minus mu square. All right? So then we also briefly talk about Chebyshev inequality. Okay, saying that the probability of x minus expectation of x greater or equal to k sigma is less than 1 over k squared. Am I right? All right, check the notes. So this is Chebyshev inequality. So what does that mean? It simply means that, okay, if I don't know how x behaves, but I know two things about this x. I know what is its expectation, I know what is its variance, or the square root of the variance. Knowing these two things, I'm able to determine a bound for this probability of x lies between, you have to understand this. This simply means that, okay, don't know what x behaves, but this is the expectation. And then it's saying that, okay, x lies, all right, mu minus k sigma and above mu plus k sigma, all right, the chance is less than 1 over k squared. 1 over k squared. So that is the Chebyshev inequality. But if you know the distribution of x, then you can compute the exact probability. Then you don't need this Chebyshev inequality. So the Chebyshev inequality is good when you don't have any information except any information about the random variable except the expectation of the variance. All right. Okay, then we move on to chapter 3, two-dimensional random variables. All right. So in that case, we start with xy. All right. So in order to know everything about this, you need to know f of xy. That means, all right, so maybe in this form, for example, it's equal to cxy, for example, x between 0 and 1 and y between 0 and 1. All right? So it's an expression involve x and y. And this expression is true for a certain range. It can be from, of course, for this case, it's like that. I can give you another example. Okay, but just stick to this one. Okay, so outside this will be 0, for example. This is a continuous random variables. All right, because x range is continuous over a continuous range, y also continuous range. All right, and cxy is a function of xy. Of course, it also, because it's a PD or probability function or probability density, it satisfies that f of xy must be greater than or equal to 0 and integrate f of xy over x over y has to be 1. It just follows similar from the one variable case. So you have this 2 over all the possible range, r squared. All right. So this, we call it John distribution. Tells you everything about the xy. So you can compute expectation of x, variance of x, expectation of y, variance of y. In addition, we have this called covariance of xy, which is to measure jointly how x and y are behaved. All right? So this is defined as expectation of x minus mu x and y minus mu y. This measures how xy together behaves. All right? So also there's another one called correlation coefficients, which is the covariance of xy divided by the square root of x and variance of x and variance of y. So this is a number, we call it correlation coefficient, and it lies between -1 and 1. And if the value is close to 0, that means xy are not highly correlated. While if close to 1 or close to -1, it means that xy are highly correlated, highly related, or have a strong linear association. All right. Now, there are two distributions arise. One is called marginal distribution, and the other one is called conditional distribution. All right? So you must be aware of what all this means. So when you have more than one random variables, then you have the joint distribution, which means how these two random variables jointly behave. So that tells you everything. But sometimes we are interested in only a part of it, like I'm only interested in x. Then I want to know what is the marginal distribution of x. So in other words, I want to find out this one. So I can find this out from the joint distribution by summing up or integrating the f of xy over y. So in other words, I basically sum up, I fix my x, I don't care about what the y is, I just sum up all the probability, the joint probability with a particular x. So I sum up all the probability with the same x but different y. So either you do the sum or do the integration. So that's the marginal distribution. And just like the events, the discussion on the events, we have conditional probability for events. We also have conditional distribution. That is f of, for example, f of x given y. All right? So this one, by definition, is the, just follow from the definition of the joint distribution. So the conditional probability, so it's the joint probability divided by the margin of y. All right? So this is something like the probability of A intercept B. This is the probability of B, and this is the probability of A given B. All right. So we condition on y. So we know that y takes a particular value. Then how does x behave? So that is the conditional distribution. All right. So we need to compute this joint distribution over the margin of y. All right. And remember, the conditional probability density function or probability function referring to one random variable x. The y, the other one, once you condition on the one on the condition part, is already fixed. So it's no more random variable. It's a constant. So in other words, in this example, the conditional distribution means that it's conditional distribution of x on given y. So y is no more a random variable. All right, because, okay, x, y here all are random variables. So we can talk about expectation of x or expectation of x given y. All right, talk about all this. So shouldn't be too difficult to evaluate those. Because if you want to evaluate expectation of x, you just have to find this PDF, the marginal PDF or marginal probability function, and then do as what we discussed in the one variable case. So for the conditional expectations, the same thing. You find the conditional distribution f of x given y, and then treat it as one variable and find the expectation of x given y. So of course, you can find variance of x and variance of x given y equal to y. All right? No, you missed the point. Why constant y? No. No. It's different thing. We're not constant y. It just add up all the y's. A very simple example. X takes 0, 1. Y takes 0, 1. 1 quarter, 1 quarter, 1 sixth. And this one, don't make it complicated, 1 quarter. Because if I change it, I may have to change others to make it work. All right? So all 1 quarter. So what's the chance of x equal to 1? It's not 1 quarter, it's not, all right? X equal to 1 can be here, can be here. I don't care about what the y is. So I just collect all the probability with x equal to 1, disregarding what the y is. So I have to collect x equals 1 and y equals 0. And x equals 1 and y equals 1. Collect all this together. So I can answer this question. It is x equals 1, y equals 0, x equal 1, y equals 0. So add up them, you got half. So then I ask what is the probability x equal to 0. Get it? And then now I treat it as one variable case. I do not fix y. Hey, to eliminate y, what I did is just add up all the, I don't care about what the y value is, I just add up the probability of those fixed x equal to that value, and then add up all the probability related to that fixed x value, but different y. So I just add up those probabilities. All right, I did not fix y. Conditional probability, you have to fix y. All right? Conditional probability, you have to look at a particular y value and then compute their probability. All right? So this one, for this simple example, it simply means that x equal to half, probability x equal to 0 is half, probability x equal to 1 also half. All right? Okay. What else then? Yeah. Okay, then we talk about chapter 4, special distribution. So we cover discrete case. We start with simple one, Bernoulli distribution, binomial distributions. For each distribution, all right, what else besides binomial? Negative binomial, we discussed that, right? Negative binomial. Poisson. Yeah, this one, a special case is the geometric distribution. Now, what you should know about all this is that you have, first of all, you have to know under what problems you can use this, or these distributions to model some problem. So, for example, binomial distribution. When we say x follow a binomial distribution with parameter np, so you have to know what x means. X means the number of successes. X represents the number of successes in n independent dichotomous trials. That means each trials you have only two outcomes, failure or success. All right, and out of these n trials, what is the number of successes? Is represented by n. All right, so the probability of success is p. So this is how x represent, and of course, you have to know what all these parameters means, what x means, what all these parameters means, and also you have to know the relationship between these parameters. So it's equal to np times 1 minus p. So not just for binomial, you have to know all the distribution we discussed. All right? Like negative binomial. If x follow a negative binomial with parameter k and p, so x represent the number of trials that you need in order to get k successes. And each trials are independent and have two outcomes only. And geometric distribution is a special case with k equal to 1. So this is a geometric distribution with k equal to 1. That means we want to know how many trials before we get the first success. All right. And Poisson also measures the number of successes, but it's not in n trials, but instead it is the number of successes within a fixed interval, or fixed area, fixed something, fixed region, or fixed volume. All right. So fix it, and then the number of success represented by n. Of course, the situation has to be, satisfy what we call Poisson experiment or Poisson conditions. All right. It again measure the number of successes, and you have to know what is the expectation, what is the variance. I think for Poisson is equal to lambda for both. All right. And then we also talk about approximation. We can use Poisson to approximate a binomial distribution. If the n is large and p is small, or 1 minus p is small. If your objective is to just find the probability of a binomial distribution, if you're a very powerful computer, you may be able to find the probability using the formula. All right, we have this f of x, right? For binomial distribution, it is n choose x, px, 1 minus pn minus x for x between from 0 up to n. All right. Now, if n is, let's say, 1 million, then how to compute? Choose, let's say, 500 out of 1 million. So it may be very difficult to compute. All right. Of course, we have maybe some other ways to compute it approximately. So the idea of this Poisson approximate the binomial is to make use of the relationship between these two. In fact, when n is big, p is large, we can show that the PDF of a probability function of a binomial is quite close to a Poisson distribution. All right? How to think about it, huh? So this is the formula, right? X factorial m minus x factorial px 1 minus pm minus x. When n is big and p is small, this come close to np to power x e to power minus np and over x factorial. But don't worry about the proof, but what I'm trying to tell you is that mathematically we can show that when n is large and p is small, then this number, which is the probability function of the binomial, come close to a Poisson distribution. All right. Okay, so we have also continuous. So for continuous, we talk about exponential, right? We talk about uniform, exponential, we talk about normal. All right. And also for exponential distribution, we talk about something called memoryless property, which simply saying that probability of x bigger than s plus t given x bigger than s is the same as probability of x bigger than t. Am I right? Yeah. Okay. So this expression is called memoryless properties, and it's simply saying that if I want to know, if I'm given that x already bigger than s, and what's the chance that x is bigger than s plus t, then it's the same as x bigger than t. This is not true for any random variable. All right? It's not necessarily true. But for exponential distribution, it is true. Okay? Yeah, normal distribution, standard normal. Yeah. So normal distribution, very important distribution, and it is mu sigma square, and you have to know this is the expectation and this represents the variance. All right. And you must know this standard normal distribution. All right. If, for example, x follow normal mu, let's say mean 3 and standard deviation 2, for example, 2 square. Then, if I ask what is the probability of x less than 1 and 5, all right? Now, to find this probability, of course, you have the graphic calculator, and then you come out the answer. But you have to understand this idea called standardization. So in fact, x follow normal with mean, mu, and variance 2 square. Okay, so x between 1 and 5, we translate it. It means that x lies within minus mu divided by 2. So 5 minus 3 divided by 2. 1 minus 3 divided by 2. So we convert to this one, we call it standard normal because it's minus mean divided by the standard deviation. This one is a random variable with mean 0 and standard deviation 1. So it is a standard normal random variable lies between 1 and minus 1. What does it mean? It means that x lies between 1 and 5 is the same as saying that, okay, I want to find the probability of x lies within 1 standard deviation from the mean. And this is very useful because it tells you some idea. What is this range? Related to the problem, I want to know how far or what is the range. The range is 1 standard deviation, all right, above and below, within 1 standard deviation of the mean. So that's what we can describe this one, instead of x between 1 and 5. All right? So that's the standardization or standard normal thing. So again, we can use this normal approximation to approximate binomial distribution. But in this case, we want n to be large, but then the MP is reasonably symmetric, or the P is not so extreme. So that means P is about in the middle, half, or in the range, in the middle range. Then the approximation is good. And of course, there's this continuity correction. So sometimes when you approximate a discrete distribution by a continuous, then you want to make the correction so that the approximation is slightly better. So you have to worry about the continuity correction. All right, then the chapter 5. Now chapter 5, so we talk about populations. There's something that we're interested in it, and all the populations, we can describe it as from a distribution. The distribution represented by a random variable. It follows certain distribution, all right? And there's some parameter, all right, follow certain distribution. Let's say normal, for example. All right. Then we take a sample, and we want to know something about the parameters such as mu and sigma square. Or maybe make it simple, just mu. All right. So we are interested in getting something like mu x bar. All right. So you look at the population. Of course, if you are able to find everyone in the population, then you can get the expectation of x. That means you can get the mu. The problem is that we cannot find everyone, or we cannot get everyone. If infinite, how can we do it? All right. So in that case, we have to take a subset. All right. You have to do it properly. You have to do a random sample. Okay. Select a subset randomly, so to guarantee that this makes sense or can be used for statistical inference. So we take a random sample, calculate the average x bar, and then use it to guess or to predict or to estimate mu. Estimate mu. So that is the idea. So, but when you take different samples, you may have a different x bar values. All right. So therefore, x bar can take infinite possible values. We can take infinite samples, and then each sample will give you one x bar value. All right. So therefore, x bar becomes a variable, and also associated with it should be a measure of the chance of it take that value. So we consider x bar as a random variable. Or you can consider taking a sample is like that. All right? I take a sample of n, so first one represented by x1, and second one represented by x2, and so on. So x bar is just 1 over n, x1 plus up to xn. So we do that. All right, so x bar is a random variable. So if it's a random variable, it makes sense to ask what is its distribution, what is its expectation, what is its variance, and so on. All right? So we know that for x bar, we can show that expectation of x bar is equal to mu, or equal to expectation of x equal to mu, and variance of x bar is equal to variance of x over n, or sigma square over n. All right? This is true. This is always true, provided that x bar is the sample mean, or that means x bar equal to this one, where each of this xi in fact is the expectation of x. x1 is taken from here, so the behavior of x1 is just any x in the population. So it should be follow the population distribution, x2 as well, x3 as well. Right. So in fact, the distribution of all this, okay, let me just take it as normal. So this one is normal mu sigma square, x2 is normal mu sigma square, and so on. All right? Okay, let me ask you, if x1 is normal mu sigma square, x2 is normal sigma mu sigma square, does x1 equal to x2? Or do x1 equal to x2? No. Why? They are from the same distribution. So I want you to make sure you understand this distribution is to describe how this x1 behaves. All right? So x2 also follow the same distribution. That means I can use the same distribution to describe x2. But when I take the sample, I observe what x1 is. All right? And what x2 is. So x1 and x2 should not be the same. Just like I toss a coin. I know the outcome is either head or tail. So the first time I toss, I got an outcome. I call it x1. The second time I toss, I call it x2. Does x1 equal, to x1 equal to x2? No. We don't know, right? So it may equal, it may not equal. So the same applies here. So I say that they have the same distribution does not mean that they must be equal. All right, x1 does not equal to x2. All right? So don't think that because they have from same distribution, so x1 plus up to xn becomes nx. No. All right? This x1 plus x2 simply means that you are adding the outcomes of these two, and these two outcomes may not be the same, so it cannot be x, cannot n times x. All right? So this one is not true. Okay, so right. Then we have this called law of large numbers. All right. So it's saying that for x bar minus mu, all right, greater than any epsilon, and the chance is approach to 0, the weak law of large number as n goes to infinity. Okay, write it in a mathematical form, but basically it's saying that if you're getting your sample size bigger and bigger and bigger, so the chance that your x bar, all right, or the difference between your x bar and mu, the difference, that means your answer, your guess, your estimate from your big sample, and the true answer, which is mu, the difference is the chance of your difference, the absolute difference, is greater than any number epsilon. It's almost close to 0. So I can choose epsilon very small. Let's say, okay, I can choose epsilon 0.000001. So it's saying that if your n is big enough, then the chance that the difference between your estimate and the true answer is greater than this number is very small chance. So it's almost very close to your true answer. So in other words, this law of large numbers is simply saying that if your sample size is big enough, then your x bar should be very close to your answer, mu. All right? So that's the law of large numbers. Wow. This is a must. You have to know central limit theorem. What does it say? It says that about if you have a random sample taken from a population which you may not have any idea what the distribution, that means we don't know f of x or f of x, we don't know this. All right? What we know is the expectation of xi, which are all mu's, and variance of xi are sigma square. All right? Then we ask, what is the distribution of x bar? So the central limit theorem does not give the exact answer, but it gives us an approximate answer. It's saying that, okay, x bar, all right, minus, or x bar, approximately, or x bar minus mu over sigma over root n is approximately normal with mean 0 and variance 1. Or you can consider, I have to say approximate when n goes to infinity. Or x bar is normal, approximately normal with mean mu and variance sigma square over n. All right? And this is a very powerful theorem. Because when you compute probability, you always need to know the distribution of that random variables. So for central limit theorem, you want to know what is the x bar, but we don't know the underlying distribution, so therefore we will not able to compute or to find the distribution of x bar. But the central limit theorem provides us a tool, saying that x bar will follow approximately normal with mean mu and variance sigma square over n. And approximately, if your sample size is big. All right, so that's the central limit theorem. So, we also, I think for that chapter, we also discuss about some other distribution. For example, we talk about chi-square distribution, right? Chi-square distribution. So this basically, okay, you have to know the expectation. If x follow chi-square is equal to n and the variance of x equal to 2n. In fact, if z is standard normal, and then z square will be chi-square with 1 degree of freedom. And chi-square also have a properties like this. If you have y1 up to yk, each follow a chi-square 1 independently, then sum of yi's will follow chi-square with k degrees of freedom. All right? So these are some properties about chi-square. And in fact, we need this to illustrate that t distribution with degrees of freedom n. So it comes from the idea that if you have a standard normal random variable, and you also have a w which is chi-square n degrees of freedom, then z over, let me call it t, z over w divided by square root n will follow something called a t distribution with degrees of freedom n minus 1. So this is the base, so that this follow a t distribution. All right, this is the theory or the theoretical background or foundation for this thing, follow a t distribution. we'll use that in our estimation and testing hypothesis. This one, obviously, we know that it is normal 0, 1, either approximate or is exact. Exact when all the x are normal with mu sigma square. If we don't have this part, then this is approximately normal when the sample size is big. But what happens if sigma is not known? So we can replace it by S and follow a T distribution. We also have a F distribution with 2 degrees of freedom, N1, N2. And it basically is W follow a chi-square with N1, W2 chi-square N2, then W1 over N1, W2 over N2, follow a F distribution with N1, N2. And we make use of this one to get the distribution of this. So for us to all this just to lay down the groundwork for us to do inference about sigma 1 square over sigma 2 square. And mu 1, okay, this one is for us to test the case or to do inference about this quantity. This one is for us to do inference about mu when sigma square is unknown. And we have to estimate. All right? So T distribution and F distribution. Okay. Oh, by the way, F distribution has this, because it's, you can consider W2 over N2, W1 over N1. So this will be a F distribution with N2, N1. So what I mean is that this and this are just reciprocal of each other. So by taking reciprocal, then it's still a F distribution, but with the degrees of freedom swap. So there's this property. So help us to find the critical values. Okay, I don't think I have much time. So okay. Chapter 6, estimation. So for estimation, you have to know, for population, we are interested in mu or sigma square. Then we would like to know an estimator. So it's x bar. And we would like to have confidence interval. This one, I think, S square. Now, for confidence interval, we can have, okay, let me write it like this. X bar minus Z, let me use 0.95% as an example. So 0.025 sigma over root n. 0.025 sigma over root n. So this is the confidence interval. We have an upper bound, lower bound. So this is supposed to be a capital letter. It's a random variable. But once you take the sample, you compute your x bar, you substitute in, you get a numerical interval, one interval. That is considered as a realization of the random interval. So we are confident that the mu is covered by these two numbers, all right, with certain level of confidence. So that is when sigma known. How about when sigma not known? Then obviously you have to replace it by an estimate. By doing so, this change to some number from a T distribution with n-1 degrees of freedom, 0.025. So this one, x bar plus Tm 0.025 S over root n. So this interval is supposed to be bigger because this number taken from n-1 T distribution is bigger than Z 0.025. So for S square, so for sigma square, so sigma square will be estimate, S square over sigma square, n-1 All right. So this one will follow a chi-square distribution with n minus 1 degrees of freedom, 0.025. And this is chi-square n minus 1, 0.025. All right? Provided that you don't know mu. Mu is unknown. I did not discuss what happens if mu is known. Do we still use S square? We should use this. Right? This is a square root of a normal distribution. So sum them up. This follow a chi-square distribution with n degrees of freedom. So what I'm trying to highlight is that they may be different if mu is known. If mu is known, you know the answer, you don't have to estimate mu. You don't use estimate by x bar. So because of that, I use mu. So in that case, it's no more chi-square n minus 1. In fact, it's chi-square n because it's just a standard normal. You sum a bunch of standard normal. How many of them? N of them. So it's chi-square n degrees of freedom. So you follow the idea and then you arrange it, you will get the confidence interval. It's similar to this part, except now you have to change this number, and also in the middle you have to slightly change to this part. All right? So that is for mu is known. Okay, so we also have this mu1 minus mu2, right? And sigma 1 square over sigma 2 square. So naturally we will consider this, we will consider this. And then the confidence interval depends on what you know. For example, when sigma 1 sigma square are known, then what to do? And when they're not known, then what to do? So whether they are known or they're unknown. And there are scenarios that they are unknown, but we know that they're equal. Although I don't know what they are, but I assume that they're equal. Then we have this formula that is to have a formula combine S1 square and S2 square to estimate the common value of this. So we have that formula. All right? So that is for confidence interval. Oh, and yeah. Oh, there's this one sample. Sorry, this paired scenario. That means although I see x and y, all right, but they're not from two independent samples. They are from the same set of individuals. But let's take two observations. One is x, the other is y. So that's called paired. So in that case, you should use a pair t-test. So the same, whether you know the variance, whether you don't know variance, and so on. All right? What else? Oh, in fact, there's one very common question asked about from other people on statistics is to how to compute the sample size. So I think we also discussed how to compute the sample size. In order to compute the sample size, you cannot just give answer. All right? You must specify the conditions. So what are the conditions? You must specify how much error that you want to accept. All right? We call margin of error. So a simple example is like this. Okay, I want to do a survey and see what's the percentage that favor my policy, for example, P. So unless I ask everyone in the population, if I cannot do that, I will ask a subset, a group, a random sample. So how many of them favor, so I work out the percentage in that sample. All right? So I want to know, okay, based on this sample, and then I want to know the margin of error. That means my estimate and the true answer, the difference between these two should be within, let's say, a certain percentage. Let's say 3 percentage point. All right. So I specify the error that I accept. But I cannot say that, okay, must be within 3 percentage point 100% of the time. You cannot, you never can able to do that. So I need to attach a probability to it. Okay, I want to have 95% chance that the error, the margin of error, that means my estimate and the true answer, the difference is within 3 percentage points. All right. So I specify the margin of error. I specify the confidence that I want, or the probability that the margin of error is less than this 3 percentage points, all right, with certain probability. So also the sample size calculation also depends on how good, how variation of your data. If your data vary a lot, you need a bigger sample size. So if you go back to check the formula depends on these 3 things. All right, depends on the margin of error. That means the difference between your estimate and the population parameters, and depends on the variation of your measurements, variance of x. Also depends on how much confidence that you want. All right. So if you want a small margin of error and you want a big confidence, the answer is that you need a very, very big sample. So for example, I want the percentage, the margin of error is 1 percentage point. All right. And then my confidence, I need 99.9%. I may need a million or a lot of data. But usually in a survey, marketing survey firm, when they do a survey, usually it's about 1,000, 2,000 for a random sample size. And they allow the margin of error to be up to 3 percentage points with certain error. So you have to know how to calculate the sample size. All right? And then for hypothesis testing, so there are some terms that you need to know, like type 1 error, type 2 error, level of significance, what else? Power of a test. All these are basic things. All right. So remember, hypothesis testing basically is you have 2 hypotheses. One, we call it null hypothesis, usually referring to the status code. That means we don't have anything to change, so that is the status code. All right. The alternative is the new statement. You want to establish some statement. So, we choose between these 2. We take a sample, calculate the sample statistics, which is similar to what we did here for the estimation. And then based on that value, you ask yourself, under the null hypothesis, is what I see here is too extreme or not? So there are 2 approaches for this one. One is to set up a fixed, we call it rejection regions. All right. So if you are observe test statistic value fall in the critical or rejection region, we make the decision to reject the null hypothesis. Alternatively, you look at something called p-value. P-value is to look at what's the chance that you see something more extreme than what you see from your sample. If its chance is very small, you suspect something wrong with the null hypothesis. Because all this p-value as well as the test statistic value are under the assumption of the null hypothesis. So if under the assumption of null hypothesis and you find that what you observe is very, very small chance, then you suspect something wrong with the null hypothesis. So just like if I want to find out whether you are a billionaire, and then I find out that you stay in a 3-room HDB flat, then the chance of a billionaire is very small. You should stay in a bungalow or condominium, stay in the city instead of stay in the suburb in Singapore. So I'm not saying that 100% you are not, but then the chance is very small. So the idea of hypothesis is like that. I'm not saying that the null hypothesis is false, but the null hypothesis is true, and the chance that I see something like that I saw in the sample is very small, so I suspect wrong with the null hypothesis. So that's the basic idea. But you have to know what is the test statistics and how to decide, make the decision. So all these are in the notes. So you just have to revise it. All right? And I think that's about it. All right? So, okay. So if you have any questions, you can make appointment to have consultation. When is the exam? You don't know? I don't know, you don't know. I don't know, it's okay. You don't know, it's not okay. Huh? Sorry? 7th. 7th of May. Thank you. All right? So remember, 7th of May. So if you have no questions, then I see you 7th of May. All right? Yeah. Okay. So thank you for the support that you gave. All right. Until the last lecture. All right. Thank you. Also say goodbye to those watch webcast regularly. And also those who just watch the last episode of the webcast. Yes, this is the last episode. Tomorrow we don't have any lecture.